So I'm going to teach a little bit of a lecture that comes from Stat 337, which is Introduction to Medical Statistics. So if you were in this class, we would have just covered case control study design. So this is a particular medical study design. This is not going to work for me. Where we select subjects into our study based on their disease status. So we get a group of subjects who have a particular disease and a group of subjects who don't have a particular disease. And then we classify them based on whether or not they had some particular exposure. And we can summarize all of this data in a 2x2 table, which I'm going to call O for observed. And we can sum up our total number of cases and total number of controls. And so our goal is to determine if there's an association between the exposure and the disease. So these happen all the time in the real world. And one such example might be the cronut burger. So as you may have heard in the news, there was this cronut burger at the CNE, and a whole bunch of people got sick. So we can't use the other medical study designs that we've already learned about in this class because we didn't anticipate going in that maybe the cronut burger was going to cause a problem. So we couldn't randomize people to eat the burger or not. We didn't think of betting a group of exposed and unexposed subjects. So instead, we're going to do a case control study. So I read the Toronto Public Health press release. And apparently, they managed to talk to 150 people who got very sick after a visit to the CNE. So they interviewed them. Our exposure is going to be having eaten the cronut burger. 79 of them had eaten a cronut burger at the CNE, and 71 had not. So they hadn't had the cronut burger. Okay, so this is our real data. They didn't publish anyone else that they had talked to, so I made up some data. That's a liberty I like to take from time to time. So I'm going to imagine that I got a random sample of 250 people who went to the CNE on the same day and didn't get sick. And I'm going to ask them whether or not they had the cronut burger. And an imaginary 45 of them did eat the cronut burger, and 205 did not. So now we work for Toronto Public Health, and we have to figure out, is this important? I mean, obviously, it's not if you eat the cronut burger, you definitely get sick. It's not that simple. And not everyone who got sick ate a cronut burger. So the question is there an association between the two? And so in our previous class, we learned about calculating odds ratios. And so you can do the calculation if you know the formula. The odds ratio for this table is 5.07. So the odds of exposure to the cronut burger are 5 times higher in people who got sick than people who didn't get sick. And 5 is a big number, but is it that big? We don't know, right? And odds ratios depend a lot on our total sample size. Here we have 400. So we need a more formal way of determining if there's actually an association. So we're going to learn how to do a formal hypothesis test. And the question we want to answer, or the null hypothesis we want to test, is there an association between exposure and disease? So our null hypothesis is actually no association. That's equivalent to an odds ratio of 1. If the odds of exposure are the same in the diseased and the non-diseased, then we get an odds ratio of 1, and that would mean there's no association. And our alternative is that there is some association. Now we're going to do a two-sided test, so we don't care whether the odds was more likely if you ate the cronut burger or less likely. So we're just going to say that there is some association between the exposure and the disease. So that's what we want to test. So here's our plan. And we're going to go through it using this data. To start off with, I'm just going to assume the null hypothesis is true. I'm going to assume the null hypothesis is true, and the data is going to have to prove me wrong. That's the way that I'm going to work. And the first step is I'm going to calculate a new version of this table with expected cell counts under the null hypothesis. So we're going to calculate the expected frequencies Now, the null hypothesis of no association means independence. So my rows and columns are independent. The probability that you're exposed has nothing to do with the probability that you have the disease. So if that's the case, the probability ij, so the probability you're in one of these particular cells in the table, is just going to be equal to the probability that you're row type I times the probability that you're column type J. So just the probability of exposure versus the particular disease probability. And we're going to estimate these. We don't have much data. So the best way to estimate the probability of being exposed would be by the number who were exposed divided by the total. It's the maximum likelihood estimator, but we don't really have to do a lot of likelihood to find that out. So we're going to estimate row probabilities by row totals and column probabilities by column totals. So the expected cell count then, and let's just do 1, 1. So the expected number of individuals who had the exposure and had the disease under our null hypothesis is going to be n times the probability of being in that cell, which is going to be n times the number exposed over n times the number diseased over n, which works out really easily to just my row total times my column total over n. So maybe I'll put some row totals here. 124 and 276 are my column totals. So my expected number here is going to be 124 times 150 over n, which is 46.5. So I would have expected 46.5 individuals to have had the disease and gotten sick if there was no association. All right. So we could do that calculation for all four cells, and we would get our expected data, which is 46.5. That's the one we calculated. 77.5, 103.5, and 172.5. fun little check you can do. Your row and column totals need to be maintained in your expected data. So if they're not, something has gone wrong when you've done your expected data. Okay, so we have observed and expected data. We want to know if no association makes sense. We're going to compare those two tables. So next, we're going to calculate our test statistic, which is just a comparison. So I'm going to tell you the formula for the test statistic. We're going to take all the differences between the observed and the expected cell counts, square them, because we like positive numbers, and divide by the expected count in each cell. So that's how we're going to compare the two tables. And not in this class, but maybe in Stat 330 or 450, we would learn that that has a chi-square 1 distribution for all of the possible tables that would relate. So if we do this calculation here, comparing those cells, the value is 52.67. This is always going to be positive. Big numbers mean we're further away. The two tables are further away. So big numbers would give evidence against the null hypothesis, and small numbers would agree with the null hypothesis. So the question is 52.67 big? The answer is, for a chi-square 1, yes, because that's the PDF of a chi-square 1 distribution. And this value here, 3.84, has only 5% of the area under the curve to the right of it. So if we get a p-value, here, the probability that a chi-square 1 is bigger than 52, that's going to be less than 0.001. So there is less than 0.1% chance that we would have gotten this data if the null hypothesis of no association between the cronut burger and getting sick were true. We actually can't say that the cronut burger makes you sick in this particular case, because we've only tested association, not causation here. But less than 0.1% is sure as heck enough to stop selling cronut burgers. Okay, and that is hypothesis testing.